No, sorry, just a minute. So what I'm going to talk about today is about the second semester course that you will take in year 2, which is called Statistical Methods. And so in that course kind of follows up from what I have taught you this semester. So before I go into that, let me summarize. I mean, in the last 2 classes this week, I don't know whether all of you guys were here, but in the class yesterday and the class day before yesterday, I talked about what you will learn in probability 2 and how it follows up from what we did in Intro to Statistics. So in the 2 classes today, that is the class from now to noon and then from 1 to 2 p.m., I will talk about statistical methods. So statistical methods is a year 2 course. So year 2 semester 2 course. Okay. And it's many of the things that you will, well, some of the things you will talk about in this course are extensions of what we learned in Introduction to Statistics, right? So in particular, one thing you will talk about is in particular, one thing you will talk about is about maximum likelihood estimation, which is what we talked about in Intro to Statistics. You may recall. So you may recall, just to refresh your memory. Let me go over the one parameter. You may remember this from the weeks before the Easter break. One parameter MLE. So suppose you have a random sample from a population with the PDF given by this, where theta is a parameter. Okay, the MLE, the procedure for update the procedure for getting MLE of theta can be obtained as follows. Okay, the first step, I mean, I think you probably remember this from what we did. The first step is to write down the likelihood function, which is the product of the density function over the n data points. The second step is to take the log of the likelihood. which is the log of that, which will be, excuse me, okay. And the third step, part C, is to take the derivative of the log likelihood with respect to theta and set that to 0, okay, and let theta hat be the root of this equation. Okay. And the final step, D, is that theta hat is it's an MLE of theta if the if the second derivative at theta equal to theta hat is negative. So this is the four-step procedure I talked about early on in the course, right, for finding a maximum likelihood estimator for theta. And you probably remember this. I mean, we did a lot of examples on this. I think, I mean, I can, well, as a reminder, let me do one example. Just one example I would do, just a reminder. Okay, example. I think this is an example I did in the course a long time ago, but I will just to remind your memory. Let me try to redo this example and then go on from it. Okay. So suppose suppose you have a random sample which are IID from the exponential distribution with parameter theta. And suppose we want to find the MLE of theta, right? So the first step, using the four-step procedure, the first step is to write down the likelihood function, which is the product of the density, which is, you know, the density of exponential, which is theta, excuse me, sorry. Yeah, theta xi. Okay. If you take the product of this, you get theta power n ef minus theta times the sum of xi. Okay, so this is the likelihood. And the second step is to take the log of the likelihood, which is n log theta minus theta times the sum of. So that's the log likelihood. And the third step, step C, is to take the derivative, which is n over theta minus sum of xi. Okay, and you set this to 0 and solve for theta. And if you do that, you get theta hat equal to n divided by the sum of xi. same as 1 divided by the sample mean x bar. Okay. Now to make sure that this is a MLE, you need to do the second order derivative. So that's the fourth step. All right, and this is clearly negative. So hence, theta hat okay, guys. So this is an example that we did a long time ago. You may recall. Okay, and now what I'm going to show you is that this procedure does not always work. And because okay, let me try to consider an example. Okay, this four-step the four-step procedure doesn't work when you have distributions. Sorry, excuse me. Right. I will explain in a minute what I mean by this. Excuse me. I will explain in a minute what I mean by this. But to explain this, let me try to do an example. All right. So example 2.
Hello, sir.
Hello.
Yeah, I'm fine.
Okay, let me try to do an example 2, just to illustrate this point, right? So suppose you have a random sample x1 to xn from a uniform distribution on the interval 0 to theta. And suppose we want to find an MLE MLE of theta. Okay. So according to the four-step procedure, which I just outlined, which I just reminded to you, the first step is to write down the likelihood function, which is the product of the density function, okay, which is 1 divided by theta power n. Okay, that's the first step. The second step is to take the log of the likelihood, which is minus n log of theta. And the third step is to find the derivative, which is minus n over theta. And if you set this to 0, then the solution for theta, or theta hat, can be either plus or minus infinity, which doesn't make sense because I mean, you cannot have a solution which is equal to plus or minus infinity. So So there is something wrong with this approach. There's something wrong with this approach when you have distributions. Like, remember the uniform distribution. The uniform distribution on the interval from 0 to theta has a bound. The bound of of this distribution is from 0 to theta, and the lower limit, the lower bound is 0. The upper bound is theta. Okay, so this is an example where the bound, at least one of the bounds, is dependent. It depends on a parameter, right? In this case, the upper bound depends on the parameter theta. So you cannot use the usual procedure. You cannot use the four-step procedure, which I gave you in the class a long time ago. You cannot use that procedure to find the MLE. So you need to use a different procedure, which I will explain to you now. Okay, I'm gonna redo example 2 using a different procedure, right? So the first step, A, is to write down the likelihood, which is the product of the density function. But you must say that when you write down the likelihood function, you must say that I don't know whether you know this or not, but do you know the I function, guys, or no? Hello, guys, talk to me. An I function is known as an indicator function. It basically says that all the xi's, the data, must lie between 0 and theta. So if you don't know this, I would write it down in a red box. Okay, an I function is known as the indicator function. You should. I hope you know this. I don't know. It's known as the indicator function. Okay, and it's defined as follows. It's defined as, it takes two values, either 1 or 0. 1 if A is true, and 0 if A is false. Okay, guys, so this is the definition of the I function. So in this example, guys, the I function takes the value 1 if xi is between 0 and theta, and it takes the value 0 otherwise. Okay. Okay. So you can simplify that to oh, sorry, you have questions. Okay, good to know. That's good to know. Good to know that you did indicate a function before. Thank you for letting me know. Anyway, I just wanted to remind you, in case you did not, in case you don't remember what an I function is. All right, now this is the product of the I function, I from 1 to n. Now there are rules about simplifying I functions, and one of the rules I will write down here. Okay, once again, let me use the red box. One of the rules for simplifying products of I functions is the following. Suppose A and B are constants, right? And this rule says the following, that this is equal to the minimum of xi greater than or equal to a, and the maximum of xi less than or equal to b. So this is a rule. I mean, you will talk about this in statistical methods next year in semester 2, but I mean, in any case, you may want to remember this. So using this rule, guys, you can write the term above as okay. So this is the likelihood function for theta, right? So that's the step A. Step B is to plot L of theta versus theta. Okay. Now I'm sure you guys in your semester 1, I'm sure you did you did the calculus, and one of the things you learned is how to plot functions, right? So if you plot this as a function of theta, I'll try to plot it as, I'm not good in drawing anything, but let me try. Let me try to do my best. Okay, so suppose this is the theta axis. Suppose this is the L of theta axis, right? So I want to plot L of theta versus theta. Now, according to this, the theta must be greater than or equal to max of xi. So suppose this is the point that corresponds to max of xi. Okay. Okay. So if theta is greater than, then it takes the value 1. If theta is less, it takes the value 0. So your graph will look something like this. Your graph will be up to this. It will be 0, and thereafter it will be a decreasing function. Do you see why? Do you see why, guys? I mean, this is stuff you should have learned. I mean, the function is 0 because if theta is less than the max because of the indicator function, and if theta is greater than or equal to the max, then this function is equal to 1, and what you have is 1 divided by theta power m, which is a decreasing function. So this basically here, what I have plotted here is 1 divided by theta power n, which, as you can see, is a decreasing function of theta. Okay, guys, is that clear or not? If it's not clear, just use the chat box. I will explain. I will try to explain better. So this is part B, and part C is to the part C is to identify the MLE of theta from the plot. So if you go back to the plot, guys, remember the MLE is the point where the graph is the largest. Obviously, the largest point of the graph is this one. This is the largest point of the graph, right? And the corresponding theta value is maximum of xi. Hence, the MLE theta hat is equal to max of xi. So So this is how, I mean, so whenever you get a, whenever, I mean, you will learn this in year 2, but I'm just telling you just for your benefit. Whenever you have you're asked to find the MLE of a distribution where one of the two bounds, either the lower bound or the upper bound, depends on on a parameter, you have to use this approach. So just to summarize, guys, the approach is, okay, let me, the approach is as follows. Let me try to summarize it so that you know in the future. You know in the future. So the approach it has 3 steps, not 4 steps. Okay, the approach is the step A is to write down L of theta and simplify it. Okay, that's step A. Step B is to plot L of theta versus theta. And step C is to find the MLE of theta from the plot. So this is the approach you should take whenever you get a question or problem that is asking you to find the MLE for a distribution that has a bounded support with one of the bounds or one or both of the bounds, depending on the parameter of interest, right? Okay, guys. Any questions so far, guys? So this is something you will learn in semester 2 of year 2. All right. So I just wanted to let you know in advance so that you can feel more confident when you go into taking that course next year. Right. All right. Now, okay. So I just did one example. Let me look at another example of this kind. Okay. So this is example 3. So here we have a random sample from a uniform distribution. So once again, as you can see, the lower bound and the upper bound depend on a parameter. The lower bound is theta minus a half, the upper bound is theta plus a half. Both of them depend on the parameter. Okay. So again, you need to, for this question, you need to use the revised approach, right? So the first part A is to write down the likelihood, which is the product of the density function. Remember, the density function for this is 1 divided by b minus a, which is 1 divided by b. Your b is theta plus a half minus a is theta minus a half. Okay, so that's the density function, and then you need to have the indicator function, which, as I mentioned before, the xi, that every data point must lie between the lower bound and the upper bound. Okay, you follow me? If you have any questions, please use the chat box. Okay, so this is equal to 1. It's basically 1 divided by 1, which is 1. So this becomes the product of the indicator function okay. Okay, now I'm going to use the rule I mentioned earlier. I don't know, I know some of you came late, but this is the rule that I mentioned to you guys earlier. Here we are. Where are we? Yeah, this rule. Sorry, here we are. This is the rule. The product of an indicator function of this form is equal to this. So I'm gonna use this rule to simplify the likelihood. All right. Here we are. Okay, so if you use that rule, guys, this becomes the indicator function where the minimum of xi is greater than or equal to theta minus a half, and the maximum of xi is less than or equal to theta plus a half. Okay, so this is what you get. Okay, all right. Using the rule that I mentioned earlier. So this is same as, you can rewrite this as follows. You can rewrite, you can say this is same as saying theta less than or equal to half plus the minimum of xi, and theta greater than or equal to maximum of xi minus a half. Okay. So, and you can rewrite this further. You can rewrite this further as follows. You can say this is theta lying between the maximum of xi minus a half and minimum of xi plus a half. Okay, so this is part A. Okay, and part B is to plot the function. All right, plot L of theta versus theta. All right, so which will be, let's see how we can do it. So I'm gonna show you how to plot it. Oh, come on, I'm very bad in plotting anything, but let me try to do it. Okay. This is the theta axis, and this is the L of theta axis. Okay, and suppose this is 0. Suppose this is 1. Okay, and suppose you have 2 points here. Suppose this point here is max of xi minus a half, and this point here is min of xi plus a half. Okay, and so your plot will look like, what do you think the plot will look like, guys? It will look like this. It will be, you have it will be a continuous line between these 2 points, and thereafter it will be elsewhere. Elsewhere it will be 0. Okay, so this is the plot of the graph. Plot of the likelihood function versus theta. Can you see that or not? It's basically because, remember, the indicator function says that if theta lies between these 2 limits, then it must be 1. And if it is not, it must be 0. That's because of the definition of indicator function. So therefore, the plot must look like this, right? Okay, so that's part B. And part C is to identify the MLE from the plot. Now, from the plot, you can see that the largest value of the graph is 1. In other words, the graph takes the value 1 from anywhere between this point and this point, right? So hence, sorry, excuse me. Okay. So the MLA is any point on the interval from this limit to this limit. Okay. Is that clear, guys, or not? Are you okay with this example, or if it's not clear, let me know. I'll try to go over again. So in this case, there's no unique value for MLE. So the MLE can be any point on the interval from this point, this point to this point, right? So it can take uncountably infinite number of values, right? Okay, guys. Talk to me, guys, and let me know if you have questions. I'll try to go over again. Okay, so this is the. Let me just do one example. Then I will stop for now, and then we'll restart at 1 p.m. So we'll have a break for 1 hour, and then we will restart at 1 p.m. Okay. Okay. Suppose. Okay. So here we have a random sample from a distribution that has this density where x, the domain of x is greater than theta. So the lower value is the lower bound of the domain is theta. So it's again you have a case of bounded support where the lower bound is depends on the parameter, right? So once again, you need to use the revised approach for finding the MLEs. The first thing is to write down the likelihood function. Okay, and then you need to have the indicator function which says that every xi is greater than theta. Okay. Now, here you need to, excuse me, to simplify this, you get theta power n divided by the product of xi squared, right? And then you have product of right? Okay, now to simplify the indicator function, right? You need, I mean, you can use the rule earlier, but in this case, okay, let me give you another rule, which may be easier to understand. The rule is as follows. So you should have a product. You should have a product I from 1 to n of the indicator function of xi greater than, say, a. Okay, and this is the same as saying that the indicator function of minimum of xi is greater than a. This is a, I mean, in fact, it's easy to prove all this, right? So if you use this, you can simplify the above to all right, guys, you with me? All right. Okay, so that's part A. Now part B is to plot L of theta versus theta, right? So if you plot this, what do you think it should look like? If you plot this as a function of theta, excuse me. These are stuff you must have learned in semester 1. Excuse me, sorry. So you should plot L of theta versus theta. Now, according to the indicator function, theta must be less than the minimum of xi. So suppose this point here corresponds to the minimum of xi, right? Then your plot will look like this. It will be thereafter it will be 0. Do you see why? Because when theta is less than min of xi is equal to 1, right? And the only factor that depends on theta is theta power n, which is clearly an increasing function of theta, right? When theta is greater than the min of xi, this is 0, so the whole thing is 0, right? So the function is increasing function up to the minimum, and thereafter it takes the value 0, right? Okay, so that's part B. Part C is to identify the largest point. So hence, the largest point of the graph is when theta is minimum of xi. So hence, the MLE theta hat is equal to the minimum xi. Is that clear, guys, or no? So I mean, the tricky part is to I know some of you, I don't know, you must have learned in semester 1 how to do the graphs and so on. I mean, a graph of a function. So this is so this is that's the trickiest part in my opinion. But if you can get if you can do a few examples like this, then you'll be okay. You'll be okay. All right. Any questions, guys? So after the break at 1 p.m., I would talk about how to do the MLE when you have more than one parameter, because so far we only looked at cases where the distribution has only one parameter, right, theta. Now suppose the distribution has more than one. For example, the normal distribution has two parameters, as you know, mu and sigma. So in that case, how would you do the MLE? I mean, what is the procedure for finding the MLE when you have two or more parameters? So I will talk about that when we rejoin at 1 p.m. right today. So, but before that, do you guys have any questions on the stuff we did so far today? Hello, guys. Are you okay? Hmm?
Yes, sir, we're okay.
All right, good. All right, so I will talk to you again at 1 o'clock UK time. So please rejoin me at 1 p.m. Okay. Okay, guys.
So you at 1 p.m. continue the content, right? Or you read?
I will continue this. Yeah, I will talk about two parameter MLE at 1 p.m. So I mean, so far we
Right.
yeah 1 p.m. UK
Thank you.
time. Yeah. All right, guys. So see you in a minute.
Yes, yes, sir.
All right.
Bye bye.
Bye.